In the last lecture, we had discussed about the derivation of units of volume and density and also weight from the unit of mass, length, etc. Now we had started discussion about the unit of temperature, and we had seen that temperature has three units: Fahrenheit, Celsius and Kelvin. Then we started discussion about the interconversion of these units. Okay. So we had studied that in a Celsius thermometer, if it is from 0 degree Celsius to 100 degree Celsius, then in the Kelvin scale, we will have it from 273 Kelvin to 373 Kelvin. Now let's see, if we have a thermometer of degree Fahrenheit, what will be the range of temperatures? So, starting temperature in degree Fahrenheit. So, degree F is equal to 9 by 5 into degree C. So, here degree C is 0, okay. So, 0 plus 32. So, this term becomes 0. So, the starting temperature in Fahrenheit scale will be 32 degree Fahrenheit, okay. Now, ending temperature in degree Fahrenheit. What will be it? So, it will be 9 by 5 into 100 plus 32. So, this is 180 plus 32. So, 212 degree Fahrenheit. So, the temperature range in Fahrenheit scale will be 32 degree Fahrenheit to 212 degree Fahrenheit. So, if someone asks that what is the freezing point of water in Kelvin scale, we can say easily that it is 273 Kelvin. If we ask that what is the boiling point of water in the Fahrenheit scale, then it is 212 degree Fahrenheit. So, this is how the unit conversion is done. Another important thing is the room temperature, okay. Generally, in all scientific measurements, the room temperature is considered to be 25 degree Celsius, okay. Not always this value matches with the original room temperature. Obviously, the room temperature in every room in the world cannot be 25 degree Celsius, but for the purpose of convenience in mathematical calculations, we consider room temperature as 25 degree Celsius. So, what is the room temperature in different units? So, let's say in degree Fahrenheit, it will be 9 by 5 into 25 plus 32, okay. So, this is 45 plus 32, 77 degree Fahrenheit. This is the room temperature in degree Fahrenheit. Now, in Kelvin. In Kelvin scale, we know Kelvin is equal to Celsius plus 273. So, 25 plus 273 is equal to 298 Kelvin. This is the room temperature in Kelvin scale. Now, in both degree Celsius and degree Fahrenheit, temperature 0 is possible, okay. So, 0 degree Celsius and 0 degree Fahrenheit are possible. Even sub-zero temperatures are possible in Celsius and Fahrenheit scale. We talk about sub-zero temperatures in Celsius, right? For example, minus 10 degrees Celsius, minus 30 degree Fahrenheit. These are possible. But Kelvin scale cannot exist below 0. Okay? So, Kelvin scale cannot exist below 0. Kelvin hypothesized that at 0 Kelvin, okay, this will be called absolute 0. So, this is the temperature where all molecular motions stop. All molecular motions stop in this temperature. Okay. So, this is called the absolute 0. So, temperature doesn't exist below absolute 0, and even absolute 0 is kind of hypothesized. So, we have studied about units and unit conversions. Now, how were these units kept in the first place? Okay, what is the reference or what is the standard measurement against which these units have been kept? So, for every unit there should be some reference standards. Reference standards are necessary so that we can calibrate the measuring instruments against it. Okay. So, scientists needed to define some reference standard against which all the measuring instruments can be standardized. Like, what is 1 kg? Okay. For example, I can say that the weight of a cricket ball is 1 kg. Someone can say that the weight of a brick is 1 kg. But this does not make anything standard. So, we need to have a particular reference standard which can be followed all over the world. So, these are called reference standards. Now, we will study about reference standards. Okay. So, there are some very famous examples of reference standards. So, the reference standard for mass. Okay. So, there is a platinum iridium cylinder kept at International Bureau of Weights and Measures. Okay. So, there is a platinum iridium cylinder which is kept at International Bureau of Weights and Measures, and all the weighing balances, all the analytical balances are calibrated against this cylinder. Okay. Mass of this cylinder is considered to be 1 kg. So, every other measuring instrument is calibrated against the weight of this cylinder. So, what we consider to be 1 kg is the mass of this cylinder, and it is followed all over the world. Now, platinum iridium is chosen because it is a very high resistant alloy, that is, it is very highly resistant to any kind of chemical changes, and its mass will not change for a very long time. So, of course, we need some reference standards which will not change with time, or at least which will not change very quickly. Now, this is the reference standard for mass. There is the reference standard for length as well. So, reference standard of length was changed from time to time. Okay. Reference standard for length. So, initially it was defined as the length between two marks on a platinum iridium bar kept at 0 degree Celsius or 273 Kelvin. Okay. Again at the same place, International Bureau of Weights and Measures. Okay. This is in France. Okay. This place is in France. So, initially the reference standard for length was the length between two marks on a platinum iridium bar. Again, platinum iridium is used because they are resistant to chemical attack. Then this definition was changed in 1960. A new definition of meter was introduced. Okay. So, this length between two marks, this is 1 meter. Okay. Now, in 1960, the definition of 1 meter was changed and it was defined as 1.65076373 into 10 to the power 6 times the wavelength of light emitted by a krypton laser. Okay. So, the second definition was this many times the wavelength of light emitted by a krypton laser. But again the definition was changed in 1983, which is still followed. So, in 1983, 1 meter was defined as the length of path travelled by light in vacuum in 1/299792458 of a second. Okay. So, this was the newest definition of 1 meter. So, the path travelled by light in vacuum in this fraction of time, it was defined as 1 meter. Now, these numbers are very random numbers, but it is as it is. So, these are the reference standards. Now, when we measure something in scientific experiments, it is not always accurate. Okay. Errors occur in scientific experiments that can be due to various causes. It can be instrumental error, it can be human error, like when we are humans, so whenever we do something, it is never perfect. So, there are human errors, there can be instrumentation error also. General instruments can show some error due to time, degradation, temperature, atmospheric changes and many things. And there are again some unavoidable errors, like how perfect your instrument may be working, or you can take many precautions while working, but still there will be a certain amount of error which is unavoidable. So, almost always the experimental value and the theoretical value have some difference. It's not a huge difference, generally it's a difference in decimals, but still a difference is there. This is called uncertainty in measurement, and there are various ways to define these uncertainties in scientific terms. So, now we will study about the uncertainty in measurement. Okay. So, there is always a difference between theoretical and experimental value. Okay. Due to the measurement of these uncertainties, we need to accept certain ways of writing a scientific result. Okay. So then first we will study about scientific notation. Okay. So, in chemistry, sometimes we have to deal with very large or very small numbers. Let's say we are talking about this number. Okay. There can be far more zeros, okay, like 20 or 40 zeros can be there. So, every time we write something, it is very inconvenient or very difficult to write as many zeros. So, to avoid such things, there is a way of writing which is called the scientific notation. We write them in the exponential terms. Okay. Let's say this is the number. We can write these as, how many zeros are there? 1, 2, 3, 4, 5. So, we can break it here and we can write as 24 into 10 to the power 5. Okay. This is the exponential term. Now, the scientific notation says that the whole number term that we are taking shouldn't have 2 digits before decimal. Okay. We will take 1 digit. Okay. So, we will write this as 2.4 into, now if we are taking single digit before the decimal, then 24 is equal to 2.4 into 10, okay, into 10 to the power 5 was there. So, we can write this number as 2.4 into 10 to the power 6. Okay, this is the scientific notation of this number. Now, let's say we have 0.00023. Okay. So, how will we write this? So, after decimal, how many zeros are there? 1, 2, 3, 4. So, we can write 1, 2, 3, 4 and 2 is in the 5th position. So, we can write 2.3 into 10 to the power minus 5. Okay. 2.3 into 10 to the power minus 5. So, these are the ways to write scientific notation. Now, if we are writing numbers in this way, then we will also have to perform the mathematical operations using this method, such as addition, subtraction, multiplication, division, etc. So, in the next lecture, we will study how to use mathematical operations on the scientific notations. Thank you.